Okay, so this is our second video in our Parabolas unit. The first video was really just a bit of a review of what it is that makes a function quadratic, so something with the highest power of x is 2. And we really just explored a little bit of the sort of algebra around quadratics, tying in also reintroducing some function notation. So what we want to move on to now is looking at the graph. So in the previous video I did talk about the fact that every single quadratic function or quadratic equation, when we draw its graph, gives a parabola. Okay, so the shape of the graph is called a parabola. The type of equation is a quadratic equation. Okay, so being clear about that distinction too. What kind of function is it? It's a quadratic function. What does its graph look like? It's a parabola. Okay, in terms of what kind of function is it, the answer isn't a parabola. The shape is a parabola. The function type is a quadratic. Okay, so let's start off together here today. In this video, I'm going to ask you to pause the video at some point and continue to work through the steps yourself, drawing some conclusions, and then I'll come back and we'll sort of bring the ideas together. But I do want you to explore the graphs yourself first and then come back to the video. So let's start off together though, just establishing our basic shape. So as I said, every single quadratic function produces a parabola when graphed. Okay, the most basic quadratic function is y equals x squared. So remember in the previous video we talked about quadratic functions being functions of the form y equals ax squared plus bx plus c, where a and b and c are numbers. B and c can be anything, a can be anything other than 0. So the quadratic function that we're looking at here is the one where a is equal to 1 and b is equal to 0 and c is equal to 0, which gives us y equals x squared, the simplest possible quadratic. Okay. Alright, so let's complete the following table of values to enable us to sketch this graph. We're well past using tables of values to sketch graphs. We're just going to use it to establish the one basic shape. Then we're going to look at the various properties and patterns that happen to enable us to sketch all other graphs. Okay, so y equals x squared. When x is 0, let's start in the middle. When x is 0, 0 squared is 0. So when x is 1, 1 squared is 1. When x is 2, 2 squared is 4, so y will be 4. When x is 3, 3 squared is 9, so y will be 9. When x is 4, 4 squared is 16, so y will be 16. And when x is 5, 5 squared is 25. Over on the negative side, when x is negative 1 squared is positive 1. Negative 2 all squared is positive 4. Negative 3 all squared is positive 9. Negative 4 all squared is positive 16. And negative 5 all squared is positive 25. Okay, so what we have here is a series of points. This is the point 0, 0 on my graph. This is the point 3, 9 on my graph. If when x equals 3, y is equal to 9 for the equation, the graph goes through the point 3, 9. Okay, so let's plot the points. So we have 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, 5, 25, and we have negative 1, 1, negative 2, 4, missed that spot slightly, negative 2, 4, negative 3, 9, negative 4, 16, and negative 5, 25. And then we can join those points up with a smooth curve, because obviously we've just calculated the whole number values, but when x equals a half, for example, half squared is a quarter. When x equals 2/3, 2/3 squared is 4/9. When x equals 5 on 2, 25 on 4, so there's infinitely many points on this graph. Okay, so there is the graph of y equals x squared. Let's have a quick chat about some properties of the parabola that we want to think about. Okay, the first thing is to do with the shape, and the shape is smooth and symmetric. It's really important whenever you draw a parabola that your parabola is smooth and symmetric. Okay, so what I don't want to see are parabolas that are sort of not very symmetric. What I don't want to see are parabolas that look like V's and they're not smooth at this point. Okay, so we don't want to see these. Okay, We want to see nice, smooth, symmetric, parabolic shape. Okay? Just fix that pen size, sorry. Alright, so they're symmetric. So the axis of symmetry is a feature. We don't draw it on the graph. It's not a graph feature that we draw. But the axis of symmetry is the line about which the graph is symmetric, and in this case that would be at the y-axis. Okay, and the y-axis has an equation. Sorry, y-intercept, y-axis, and the y-axis has an equation of x equals 0. Okay, that is the line x equals 0. Every point on that line has an x coordinate of 0. So it has an axis of symmetry. It also has a turning point at 0, 0. Okay. And so the turning point's a key feature of the parabola. So whenever we draw graphs, we've already talked about, we've only really looked at linear graphs before now, but whenever we draw graphs, no matter what kind of graphs they are, we'll look at a lot more graphs this semester, but whenever we draw graphs, we must always mark x and y intercepts. So anywhere the graph crosses the x-axis or the y-axis needs to be marked. And in the case of the parabola, we also need to draw in, to mark the turning point, the coordinates of the turning point. Okay, so there could be up to 4 points to be marking on your graph of a parabola. If, for example, your parabola is over here, you would need to mark the turning point, the two x-intercepts, and the y-intercept. In this instance, if we were drawing this graph y equals x squared, if we were making a sketch of that, and we don't have our x-intercept, y-intercept and turning point are all the same point, we would actually need to mark another point on this graph just to give an indication of how stretched it is. So in this case, 1, 1. You know, just so that we can be clear about the difference between y equals x squared and y equals 2x squared, for example. We'll talk more about that down the track. Okay, so smooth symmetric, axis of symmetry, and turning point at 0, 0 in this particular case. So now that we've got this basic parabola shape, all other parabolas will be dilations, reflections, and translations of this parabola. And that's what we want to look at over the course of this video and the next video, and the next one really, where we'll combine all those together. And it's really important that we clearly establish these patterns for the parabola, because what we're going to see as we move through this semester, and certainly through the next 2 years, is that these patterns apply to all graphs. So the way that we apply a dilation to the quadratic graph is the same as applying the dilation to the cubic graph, or a square root graph, or a hyperbola, or all the other graph types that we're going to look at. So when we talk about the word dilation, dilation is a stretch, okay? And in terms of the, we would need to know 2 things if we want to stretch the graph. We would need to know the dilation factor, how much are we stretching by, and the direction of the dilation. Okay, and in this case, we're either going to be stretching vertically, which we call from the x-axis, to stretch away from the x-axis, or horizontally, which we call from the y-axis. Okay, that's the only kind of dilations we'll do. So there's 2 things that define a dilation. How much do you want me to dilate it by? How much do you want me to stretch it by? And in which direction do you want me to stretch it? Reflections, that's pretty clear. We're going to take the mirror image, but we need to know where the mirror line is. Reflection in what line? And in this case, it's either going to be in the x-axis or in the y-axis. Okay, so we're either going to mirror the shape in the x-axis or in the y-axis. And then translations is shifts, okay? So it's a shift of the graph. We've got a stretch of the graph, a mirroring or a reflection of the graph, and a shift of the graph. And translations can either go, we need to know 2 things again, how far to shift, and in the direction, which direction. And the direction will again either be horizontal, which is going to be sort of given as left or right, or vertical, which will be given as up or down. So we want to get used to talking in terms of the words dilation, reflection and translation rather than stretching and shifting. Okay, it's important we start to formalise that language. And we want to be clear about, okay, it's not enough to just say stretch the graph. That doesn't tell me anything. How much do you want me to stretch it by and in which direction do you want me to stretch it? In fact, we're going to say dilate. How much do you want me to dilate it by? What's the dilation factor and in which direction? We'll formalise that a bit more as we work through different graphs, but I want you to really start to think in those terms as we work through the parabola. So what we want to investigate over the course of this video and the next video is how we apply those transformations to the graph and what that looks like in the equation. What does putting a number 3 here do? Does it shift it? Does it dilate it? What does it do? Okay. What does it do if I stick a negative here? Does it translate it? Does it reflect it? Does it dilate it? What's happening? Okay. Alright, so we're going to use our CAS. It's really important that you've got your CAS with you here. I really want you to actually work through this and to develop some of these, identify some of these patterns yourself. So I'm just going to talk you through the first few steps just to kind of get you started. But then what I want you to do is pause the video and work through the questions and the steps and the instructions and fill in the blanks here. And then at the end, come back to the video and I'll try and bring all that together for you in a bit of a summary. Okay. So at the beginning here it says turn on your CAS calculator and press the home button, okay, to access the home page, and we're going to press number 1 for a new document, and I don't want to save the unsaved document that I've got here, so choose no, and we're going to add a graph page, so number 2. Okay, so that's the instructions in the box here that I've just followed. Okay, you've got all the instructions there in front of you on your sheet. Okay, so what we want to investigate first of all is what does the graph of a times x squared look like? So 2x squared, 3x squared, 5x squared, 7.2x squared, negative x squared, negative 6x squared. Okay, we want to explore that. So we're going to graph the line y equals x by typing x squared into the entry line. Now if you can't see the entry line when you start up your CAS, all right, you want to press tab to open up the entry line or Control G. If your entry line isn't in function notation, if it doesn't say f1 of x equals, it's really important. We only want our entry line to look like that in this subject, okay, in the next 3 years. If it doesn't, menu, graph entry edit number 3, and choose 1 for function, okay. Alright, so then you want to sketch just x squared first of all. We just want to have a look at that. Alright, so there's y equals x squared. It then says to use graph trace or analyze graph to explore this graph. So menu 5.1 for graph trace puts a cursor on your graph, and you can see the coordinates of that point down in the bottom right at 0, 0, and then we can move around the graph and have a play and see what's happening here. Okay, so you notice as I scrolled past the window, it increased the size of the window. Alternatively, you could, menu 6.1 use analyze graph to perhaps explore, menu 6 and play around with finding the zeros or the minimums or the maximums. This graph doesn't have a maximum, it has a minimum though, 2. So somewhere to the left of that point and somewhere to that right of that point, you can play around with that. So I just wanted you to explore the parabola for a minute. Okay, then let's explore what happens if we look at ax squared. So I'm going to insert a new graph page into my document. So I'm going to press Control I, and I'm going to press number 2 to make it a graph page. So now you see at the top I've got 2 tabs. I've inserted a second tab. If I want to get back to the first tab, I can just press Control across to go back to the first tab, Control across to go to the next tab. So these are all in the same document. I don't usually instruct you to work in document mode because I think it's problematic. You can build up too many pages here and it becomes really untidy. But for this I want to establish a number of pages within the same document. Okay, so the graph entry line is already automatically opened up for me. If it hasn't for you, press Tab or Control G. You'll see that it's now at function 2. If I scroll up here, function 1 is here. That's the function from the first page. So this is one of the issues with documents, is that you can access the information from all of your pages in any page. So I'm on page 2, but I can still access the equation I defined on page 1. Now, in normal everyday use of our CAS, we don't want that. We don't want that build-up of information. So that's why I encourage you to work in the scratch pad usually. But today we want that sense of build-up. So now we're going to add another graph, function 2, and this time it is going to be a times x squared. It's really important that you type the multiplication, because otherwise your graph doesn't see it as something times x squared, it just sees it as a variable that's called x squared. Okay, so you must enter in the multiplication between the a and the x squared. Okay, when I press enter here, it's not going to know what to graph because it doesn't know what a is. Okay, how can it possibly draw a graph if I don't tell it what number to put there? But when I press enter here, your CAS will ask you, would you like to create a slider for a? Okay, and in this case I do, so that's going to allow me to create a little slider that I can then adjust the value of a. So yes, we do want to create a slider. If your CAS didn't ask you how to create a slider, there are steps below here for, if your CAS didn't ask you if you wanted to create a slider, there are steps below here to do that. My apologies, I skipped a step here. So the other thing I want to do here, just to help us explore and see the patterns of what's happening, I want to add a grid to my axes. So I'm going to press menu, 2, 6, 3. So 2 is view, 6 is grid, and 3 is aligned grid. Okay, so we're just going to add that. It's going to help us to kind of see what's happening here. Alright, so I've now added the grid, I've sketched ax squared, I've got my slider. Okay, so now let's go into here. So we can skip the step which is about inserting the slider because we've already inserted the slider, and we don't need to place the slider, it's already been placed, and we don't need to type a in the slider, it already represents a. Okay, so we're going to start at this point here if our CAS asked us to insert the slider. So if you need to move your slider, you hover over the slider. My apologies. You take your cursor and you hover over the slider, and you'll see, now yours will be bigger than mine is, but you'll see that the cursor became a hand as I moved onto the slider, and it's an open hand. If you now click the middle button of your click pad, okay, so the button that's just become red there, if you now have to do it slightly differently on the computer, if you now, sorry, let me just undo that. Sorry, 3, no, 2, 6, 3, sorry, I lost my grid. Chaos. All right. If you want to move your slider, I'm having I can't do it on here. I'm having trouble with this because it's a bit different on the computer. So the cursor became a hand. Okay. You want to then click the center of your click pad. That's where things went wrong for me. And click and hold it. And when you click and hold, the hand will close up. You'll see the hand, the fingers of the hand will close together, which means you've picked up the slider. You can then, as you move your cursor, the slider will move with you, and then you just click the middle of your click pad again to open up the hand and release and drop the slider in the new position. So if you want to move it, that's how you do it. Okay, so you've got your slider. Now we want to hover over or click on the slider so that our cursor becomes open hand, and we're going to right click. Okay, so for you to right click, you click control menu on your keypad, and then you're going to choose, now sorry, that says number 1 settings. I think yours could be different. Yeah, that's better. It's because I'd had that problem with the moving. Okay, number 1 settings. And we're going to make sure that the settings are as you can see in this list here. Okay, so the variable is certainly a. The value I want to be 1, that's okay. The minimum value is going to be -5. The maximum is going to be +5. The step size, I'm going to edit that. I'm going to make that 0.5. And I'm going to make the slider style vertical. It doesn't really matter if you don't change the style, but let's do that. I'm going to leave the other things, and I'm also going to tick the minimized box just to make my slider a bit smaller. It's also a bit easier to work with in your CAS, in your handheld CAS. Okay, so we're going to go with minimized. We're going to go OK. Alright, so now my slider should look like this. I've got vertical arrows rather than an actual sort of scale. And we want to think about, okay, what is the equation of the graph that we can now see on the screen? So we can see that our graph is y, remember this is function notation, it's y equals ax squared, and we can see from our slider that a is 1. So actually the equation that we are looking at here is y equals 1x squared, so just y equals x squared. Okay, so then the notes instruct you to press the up arrow of your slider to increase the value of a, and describe what happens as you increase a. So I want you to do that. Play around with your slider, press the up arrow, describe what you see happening as you increase the value of a. Okay, then it says decrease the value of a to 0.5, 0.5, and describe what happened to the graph. Okay. And then it asks you to think about, okay, what would the graph of 3x squared look like? What would the graph of a quarter x squared look like? Thinking about what you've described as happening here. Also, you could use your CAS to make the a value 3. You could use your CAS to make the a value, well, actually, I changed the slider so that you couldn't make it a quarter. So think about what will happen with a quarter, okay? You can also adjust your window if you want. Remember, if this is a bit too far, this -10, where sort of everything's a bit cramped, I might make my window just -5 to 5 perhaps, so that I'm sort of seeing a bit more of my parabola. I might choose to make my y values a little bigger, just to give me a better sense of what's happening, so you can play around, okay? Play around with your slider, responding to the questions here, so sketching 2 graphs on this axis here. Decrease the slider so the value of a is 0. What is the equation of the graph? What happened to the graph and why did this happen? Continue to decrease the slider so the value of a is negative. Describe what happens to the graph. Sketch these 2 graphs on this axis. Okay, I want you to work your way through that, and then you can come back and I'm going to bring the ideas together. Okay, so I want you to pause the video now and go away and work your way through this with your CAS. Okay, so hopefully you've had a play around with your graph and your CAS and the slider, and had a play around with what happens with A. I'm using a different software package here. It's just a bit nicer on the computer compared to the CAS, but I've got the same idea. I've got the graph of y equals ax squared drawn here, and at the moment a is 1, and I've got this constant controller that's going to allow me to change the value of a. Okay, so the first thing you did in your notes was you made a bigger. Okay, and you were asked to describe what happens to the graph. Now, I would bet that what most of you described was that the graph got thinner. Okay, so what you did, and I'm going to draw on this, but the drawing facility on this program is pretty poor. What you did is you suggested that the graph gets thinner, that's what happens, okay, as we make a bigger. Now, that is true, it does, but that's actually difficult because it doesn't actually directly connect to that number. So here where a is 3, okay, so what we're doing here, remember we talked about dilation, reflection, translation. This is a dilation, it's a stretch, or a squash in this case, but it's a stretch. So what you're looking, if you talk about it becoming thinner, what you're looking at here is a squash, but the squash isn't of a factor of 3. Okay, when a is 3. And so it's actually quite complicated to think about it as a squash. So I'd rather that we, oh, sorry, I need to actually delete the value, just my annotations. So I'd rather not talk about it as the graph getting thinner. Okay, what I really want you to get a sense of what's actually happening is this. The graph is being stretched away from the x-axis. Okay, that's what's happening. It's a vertical stretch rather than a horizontal squash. Okay, so the graph is being stretched away from the x-axis. Okay, let me make a whole number. Okay, so at the moment a is 3. Okay, what we're seeing here, let's look at some specific points. Let me just erase those arrows and I'll add them back in again. So what we're actually seeing here is I've kept you can still see the original parabola in black, y equals x squared. So what we've got here is this is the point 1, 1 on the original parabola. Okay, sorry, that's not 1.1, I just can't draw a comma very neatly. And what we've seen is it's been stretched away from the x-axis, and now that point is 1, 3. Sorry, I really can't draw that precisely. Let me see if I can do it smaller. 1, 3. Okay, is that point over there. Alright, so let me neaten that up. So what we've seen happen is when we made the a value 3, the graph has moved away from the x-axis by a factor of 3. And what that has meant is the y value has tripled. We'll see the same thing has happened over here. This is the point 2, 4. Sorry, again, very hard to write. I can do arrows, but writing's difficult in this program. And that has stretched away now to the point 2, 12. We've stretched away by a factor of 3. the graph has been dilated by a factor of 3 away from the x-axis in a vertical direction. Okay, and we should be able to say that for any point. You can pick any point, and what's happened is the y-coordinate has been tripled. Okay, if we made a 2, then we're doubling all the y-coordinates, and we stretch the graph away. Now we notice that the turning point's not moving, and that's because if we think about what's happening, the y-coordinate of the turning point is 0. So if you triple all the y values by stretching away from the x-axis, tripling 0 is still 0. So this point stays here. Oh, sorry, that was an attempt to erase. Okay, so what we're actually seeing happen is a stretch or a dilation away from the x-axis by a factor of a. Okay, so again, if I make a bigger, we're stretching further away from the x-axis. Now this is 4 times as big now. Okay, if we make a smaller, so the next question it asked you was to make a to make a half or 0.5. If you do that, the graph became, you probably talked about it becoming wider or flatter in your description, and that's absolutely true. But what I want us to really think about is what happens is it gets squashed towards the x-axis, okay? And again, it's about the y values have been halved because we have dilated the graph by half from the x-axis, okay? All the y values have been halved. So we've gone from the 0.24 to the 0.22, from the 0.39 to the 0.34.5, from the 0.416 to the 0.48, okay? The graph got, all the y values got halved, so the graph got flattened or squashed, but it's still a dilation. It's a dilation from the x-axis by a factor of a half. Okay, then it asked you to make a 0, okay, and talk about what happened, okay? So when a equals 0, sorry, just going to have some of those annotations floating around. When a equals 0, we no longer get a parabola at all, we get a straight line. And remember, the definition of a quadratic is such that a can't be 0. And that's because if a equals 0, the equation of the line is y equals 0, and that's a straight line. That's not a parabola at all. Okay, so it's not technically a quadratic function if a is 0, so we'll ignore that. We're going to keep moving now to when a is negative. All right, and we see now that the graph is there's still a dilating effect happening. We're able to squash it and stretch it by changing the size of a, but the negative value made the graph reflect. Okay, so we've reflected in the x-axis because of the negative number, the negative value of a. At the moment, let's make that a is negative 2, so the negative is about reflection in the x-axis, and the 2 is still about dilating by a factor of 2 away from the x-axis. So we've reflected the graph, which would bring it down to 1, negative 1, and then we've dilated it by a factor of 2 away from the x-axis, which makes it go to 1, negative 2. You could also do those in the other order. You could dilate it first, stretch it up to 1, positive 2, and then reflect it to get to this point. This graph here, we're going to dilate it by a factor of 2. It goes out to 2.8. Sorry, that's 2.9. Goes out to 2.8. And then we reflect it in the x-axis down here to 2, negative 8. Okay, so when a is negative, it has 2 effects on the graph. If it's a negative value, it's a reflection. So you can never have a dilation by a factor of a negative number. The negative is the reflection. The size of the number, the 2, is the dilation factor. Okay, so a has 2 effects on your graph. It dilates and it reflects. So back over in the notes, for example, these last two, so these 2 graphs up here, when you were sketching the graph of y equals 3x squared, you're dilating the graph away from the x-axis by a factor of 3. So you're tripling all the y values. 1, 1 goes to 1, 3. 2, 4 goes to 2, 12. 3, 9 goes to 3, 18. So we're off the chart now. It's about here. Okay. Same on the other side. 0, 0 is going to stay here. 1 goes to 1, 1, 1 goes to 1, 3. 2, 4 goes to 2, 12. 3, 9 goes to 3, 18, which is off the chart. Okay. And so we get a steeper parabola. Thinner, yes, but I want you to think about it more as being steeper and squashed from the x-axis. Okay. So this is y equals 3x squared. When you draw the graph of y equals 1/4 x squared, all the y values are being divided by 4. We're finding a quarter of them. So instead of going through 1, 1, we're going to go through 1, 1/4. 2, 4 is going to go through 2, 1. 3, 9 is going to go through 3, 9 on 4. 9 divided by 4 is 2 1/4. 4, 16 is now 4, 4. Okay, so the graph becomes a lot wider and flatter because we are squashing it towards the x-axis. So your graphs should look something like that. Okay. The second two graphs that you've drawn here, 10x squared, so that's a dilation by a factor of 10 away from the x-axis. 1, 1 goes to 110. You're multiplying the y value by 10. 2, 4 is going to go to 240. It's off the chart. Okay. So y equals 10x squared, super tall and thin. Y equals negative 6x squared. So we've got two things happening there. The negative means we're reflecting, and we're also dilating by a factor of 6. So 1, 1, we reflect it in the x-axis, goes to 1, negative 1. We then dilate it by a factor of 6. It's going to go down to 1, negative 6. And we'll have the same symmetry on the other side. Okay. So y equals negative 6x squared. Okay, so the work for today is on a worksheet, Transformations of the Parabola Part 1, and you can go ahead and do that work.